So we'll start friction today, which is a part of your module 3. So now question arises, what is friction? Okay, so what is friction? We can write that when a body moves on the surface on which it is resting, it is resting will oppose its motion because of surface roughness, because of surface roughness and surface irregularities. This opposing force is called force of friction, and the phenomena is known as friction. Is known as friction. Okay. Now coming to the different types of friction. First, we have static friction. Sorry, static friction. Then we have dynamic friction. Dynamic friction. Under this category, we have sliding friction, rolling friction, pivot friction, then basically this pivot friction um, is a friction experienced by a body a body due to the motion of rotation in case of footstep bearing. Okay. So it is further subclassified friction between lubricated surfaces, lubricated surfaces and friction between unlubricated surfaces. Unlubricated surfaces. Okay, so friction of pivot and color bearing. Out of this, we'll discuss only this friction of pivot and color bearing, because the rest are very basic which you have already covered, so I'm not going to elaborate them. So on this part, we can write that rotating shafts are subjected to axial thrust axial thrust. Okay, the bearing surface the bearing surface such as um, pivot and color bearings are used to take this axial thrust axial thrust of rotating shaft Okay, now if we look into the schematic of pivot, we have these following categories. Okay, you can see here. Let me draw it. Let's say we have a shaft and so this is the shaft. So this is known as flat pivot or pivot, you can pronounce. Then you have conical pivot like this. So this is conical pivot. See, then we have truncated pivot. It is known as truncated pivot. Okay. Now first we'll discuss about this flat pivot bearing. Okay. So coming to this flat pivot bearing. Let me draw it once again. So we'll indicate the hashed portion. So this one is the shaft, and this bottom portion is known as your flat pivot, sorry, bearing. Okay. Now if you draw the top view, it will be somewhat like this. Let's say this is the inner shaft diameter, okay, and within this, uh, this is the top view. You can write here. Okay. Now let's say a rotating shaft in a flat pivot bearing is as shown in the figure. So let this W is the load transmitted from shaft to the bearing. Now this W is acting in the shaft here. This one is the load which is transmitted from the shaft to the bearing, and R, you can say radius of bearing surface, radius of bearing surface. Okay, then let's say P, small p, is the intensity of pressure. Then mu is the coefficient of friction, coefficient of friction. Then we take actually two criteria into account. One is uniform pressure and another is uniform wear. Okay, so according to pressure uniform pressure total frictional torque, I'm not going to derive this. Okay, total frictional torque T be equal to 2 by 3 mu w r. Okay. If you have any doubt in the derivation, then in my subsequent videos I'll upload the derivation if you need. Okay, so let me know. So when the shaft rotates, when the shaft rotates at omega radian per second, the power lost in friction, the power lost in friction, that is P, will be equal to T dot omega. Okay, or you can say it is T dot 2 pi n by 60. Okay, so remember this. Let's say this is equation 1, this is equation 2. This with respect to the uniform pressure theory. What is this theory? I will let you know. Okay, then according to uniform wear, uniform wear, total frictional torque, total frictional torque T is equal to half mu WR. Okay, mu is the coefficient friction, W is the load acting in the shaft, R is the bearing radius. Okay, now suppose a question is given to you. Let's say the question, let me take it out. So this is the question. Suppose it is saying a vertical shaft of 150 mm diameter, okay, rotating at 100 rpm, raised on a flat end footstep bearing. The shaft carries a vertical load of 20 kilonewton. Okay, so W is given to you. Assuming uniform pressure distribution and value of omega is given 0.05, estimate the power lost in friction. Okay, so you can easily calculate this. Let's say first what are the given data. So we'll write the given data. First R, radius of bearing surface, bearing surface will be, shaft diameter is given 150 divided by 2, so 75 mm, so it will be 0.075 meter. Okay, then speed of shaft, n is given 100 rpm, then coefficient of friction, coefficient of friction mu is given 0.05. Okay, then load acting load acting on shaft or bearing load, sometimes we called it W, is given how much? 20 kilonewton. 20 kilonewton. Okay, so according to uniform pressure theory, uniform pressure criteria, you can say, this total frictional torque, total frictional torque T is equal to 2 by 3 mu W R. Okay, so we can write this as 2 by 3 into 0.05 into W is 20 into 10 to the power 3, okay, kilonewton, and R is 0.075. Okay, so this gives you T as 50 Newton meter. Okay, please recalculate it. Okay, now what will be the power lost in friction? So power lost in friction P will be T dot omega. So 50 into 2 pi n is your 100 rpm divided by 60. Okay, so this will give you P as 523.5 watt. Okay, this is a very simple problem, okay, that we discuss. So next is your conical pivot bearing. Conical pivot bearing. Okay, now the schematic of a conical pivot bearing is somewhat like this. Let's say this is the shaft, and this area indicates the bearing. Okay, I am not drawing it entirely, and this total angle, total included angle from here to here is denoted by 2 alpha, and the radius, okay, from here to here it is R, capital R, and the normal force acting on one side of this inclined surface, normal pressure we can say, it is P subscript N. Okay, we can say. So now I can say let, uh, as I told, Pn is the intensity of pressure, intensity of pressure, okay, normal to the cone, normal to the cone, then 2 alpha is the angle of cone. Remember this, it is angle of cone, and alpha will be semi-angle of cone. Semi-angle of cone. So use this as per your problem statement. Okay. Now mu is the coefficient of friction. Coefficient of friction, and R is the radius of shaft. Radius of shaft. So considering again uniform pressure criteria, according to this uniform pressure criteria, this total frictional torque T is 2 by 3 mu W R. Up to this it was in case of flat bearing. Now you add this term cosec alpha, so it will be easy to remember. 2 by 3 mu W R cosec alpha in case of conical bearing. Yeah, conical pivot bearing. Now considering uniform wear, and power will be same, remember P will be T dot omega. Okay. Then considering uniform wear, criteria, you have T is equal to half mu W R cosec alpha. Okay. Next is your trapezoidal or truncated conical. It is also known as truncated conical pivot bearing. Okay. So the schematic of this truncated conical pivot bearing is like this. We'll have the shaft in this way, and this is the center axis of the shaft, and the bearing part is this. So this one is our shaft, and this portion is the bearing. Okay, let's say let me change the color here. So let's say this radius is your R2 and the outer radius is R1. Okay, so you can write, in this case the total frictional torque T is 2 by 3 mu WR cosec alpha into, you'll add a term R1 cube minus R2 cube divided by R1 square minus R2 square. So remember this formula. Okay, and this is for uniform pressure criteria. Okay, uniform pressure criteria. Now considering uniform wear criteria, uniform wear criteria, your T, total frictional torque, T will be half mu W R, or instead of effective R you can take R1 plus R2 cosec alpha, okay. Or if you mention this effective R as R1 plus R2, then we can represent this T as half mu W R cosec, cosec alpha. Okay, and here this part is your effective R for uniform pressure criteria. Remember this, okay, where this or you can mention like this. Um, if you take mean mean radius of bearing, mean radius of bearing R is will be equal to R1 plus R2 by 2. In that case, T will be equal to mu W R, okay, mu W R cosec alpha for your uniform wear criteria. Remember this. Okay. Now let's solve one problem on this. Let's say it is given that a conical pivot support a load of 20 kilonewton. The cone angle is given 120 degree and the normal pressure on the cone surface is 0.3 Newton per mm square. The external diameter is twice that of the internal diameter. That means R1 is equal to 2 R2. Okay. Now find the outer and inner radii of the bearing surface. We have to find out R1 and R2. If the shaft rotates, N is given 200 rpm. Coefficient of friction mu is given 0.1. Find the power absorbed in friction. Assume uniform pressure. Okay, so you have to assume uniform pressure. So first we'll use this relation that Pn, the normal pressure, will be load per unit area. So load is the load acting on the shaft, that is W, and area will be pi R1 square minus R2 square. Okay, or we can say it is W divided by pi into 2R2 square minus R2 square. okay, as per the problem statement. So now you substitute the value. W is given 20 into 10 to the power 3, okay, because here it is mentioned 20 kilonewton is the load. So 20 into 10 to the 3 divided by uh, pi into 3r2 square, okay, 3r2 square. So now Pn is given. So substituting all values, you will get R2 equal to 84 mm. Okay, please recheck. Okay, calculate and check this value. Okay, R2 will be 84 mm and R1 will be twice that of your R2. So R1 is 168 mm. Okay. Then power absorbed or power lost in friction. Power absorbed, we have to calculate. So for this, first we have to find out the T, total frictional torque. So total frictional torque T, according to uniform pressure theory, 2 by 3 mu W, okay, mu W cosec alpha into R1 cube minus R2 cube divided by R1 square minus R2 square. So it will be equal to 2 by 3 into 0.1 into 20 into 10 to the power 3, okay, cosec 60, okay. Then because the angle is given, no, 120 degree, 2 alpha is given, 2 alpha is given 120 degree here, cone angle, so alpha will be 60, okay. So it is 168 q minus 84 q divided by 168 square minus 84 square. So T will be equal to 301.76 Newton meter. If you calculate and convert into meter, you'll find it will be coming around 301.76 Newton meter, and power absorbed P is equal to T dot omega. So 301.76 into omega is 2 pi. N is given 100 rpm, no? Yes, N is 100 divided by 60. So you will get a value of approximately 6.3 kilowatt. This much power is absorbed in friction. Okay. Now let's say another question is given. It is, suppose a conical pivot bearing supports a vertical shaft of 200 mm diameter, weight acting in the shaft 300 kilonewton, 2 alpha is given 120 degree, coefficient of friction is 0.025, speed of the shaft is 140 rpm. Find the power lost in friction using uniform pressure criteria and uniform wear criteria. So we'll see one by one. First, according to this uniform pressure criteria, uniform pressure criteria, this T, power lost in friction, will be 2 by 3 into mu W cosec alpha. Okay. So here we can choose this mean radius R. Okay. Um, so it will be equal to 2 by 3 into 0.025 into 30 into 10 to the power 3 into cosec 60 into R will be, diameter is given 200, so it will be 0.1, so it is 57.7 Newton meter. Now power lost P will be T dot omega, so 57.7 into omega, you can calculate from the n is 140, so 2 pi into 140 by 60, so P is coming around 846 watt. Okay, now according to this uniform wear criteria, we have T is equal to half mu W R cosec alpha. Here I am choosing this mean radius because no relation between the outer and inner radius is given to you, only it is saying shaft diameter. So in that case you will choose R value, capital R. So half into 0.025 into W is 30 into 10 to the 3, R you take as 0.1, cosec 60, so this will give you 43.3 approximately Newton meter. Okay, then power lost P you can calculate as T dot omega, so 43.3 into your 14.66, 2 pi n by 60 is 14.66, so this will come around 634.8 watt. So you can see the power lost in friction because of uniform wear is less than that of the power loss due to uniform pressure. Okay, remember this. Okay, when we'll discuss about these two criteria, at that time I'll elaborate. Okay, for the timing, you remember power lost in friction in uniform wear is less than that of your power lost in friction due to uniform pressure criteria. Okay. Now another question, suppose it is given that in a thrust bearing, here R1 R2 is coming into picture. R1 is given 320 mm, R2 is 200 mm, total load 80 kilonewton, normal pressure is 350 kilonewton per meter square, speed of the shaft is 400 rpm, mu is given 0.06. Okay, calculate the power lost in friction and can add here and number of colors required. Okay, number of colors required. So in this particular case, let us use the relation. If nothing is given in the figure, we'll assume uniform pressure criteria. Okay, because we'll take into account the maximum frictional torque into account, and we know from our previous problem that torque frictional torque is more in case of uniform pressure. So with respect to that assumption, let's say T is equal to 2 by 3 mu W R1 cube minus R2 cube divided by R1 square minus R2 square. So if you calculate this, 2 by 3 mu is given 0.06 and W is 80 into 10 to the power 3. Okay, R1 is 320, so 0.32 Q minus 0.2 Q divided by 0.32 square minus 0.2 square. I am converting everything into meter. Okay, so in that case, you'll get this T as 635.12. 635.12 Newton meter. And your power lost in friction P is T omega. So 635.12 into omega 2 pi n is given to you 400 rpm divided by 60. So this is coming around 26.602 kilowatt. Okay. So number of colors, now we need to find out number of colors. So in that case, it will be equal to total load, okay, divided by this Pn into load per unit color. Okay, total load divided by load per unit color. So Pn, this load will be pressure into area. So Pn into area is pi R1 square minus R2 square. Okay, so this will be equal to total load is here 80 into 10 to the 3 divided by load per unit color will be pressure into area. So Pn is 350 into 10 to the power 3, okay, into pi. R1 is given 0.32 square minus 0.2 square. So if we calculate this, it is coming at approximately 4.65 or 4.66. So round about 505. Okay. So in total, you can take total 5 number of colors so that we can withstand this much amount of total load. Okay. So this way you have to solve. In the next class, we'll discuss about journal bearing and then we'll start the color friction. Okay. So try to solve the problems.